So finally, and after actually kind of related to what we talked about with your conjugate acid-base pairs, can we talk about buffered solutions? So a buffered solution, my whiteboard's so dirty, but to me, when I picture a buffered solution, just like this says, this is my buffered solution. And I can drip H plus in it or OH minus in it, and it will, the pH will be steady. That's kind of what I picture when I picture a buffered solution. And so you're like, well, how can that happen? And the reason that can happen is because we must have something in there that will react with acid and something in there that will react with base. And actually, the third criteria is those two somethings need to be able to coexist. And some things that coexist well are conjugate acid-base pairs. So what would that look like? Well, I've got an indicator in both of these solutions. The one on the right is buffered and the other one is not buffered. So if we add then acid to it, you can see that the one that was buffered doesn't change its pH, but the one that was not buffered turns acidic. And you can tell it's acidic by the fact if you deal much with indicators. This is methyl orange, and actually it's just showing you that it turned acidic. That's why it changed colors. This one resisted pH change. So the three requirements, kind of like I said over here, in your buffered solution, you need to have something that's going to gobble up your OH minuses. And what is that something going to be? It's going to be an acid. Okay? You're going to need to have a base that'll gobble up your H pluses. And then those two things need to be able to coexist. Okay, so again, you're going to have two things down here that can counteract whatever you're going to throw at it. That's it. So almost always what you have then, the two things, is you have a conjugate acid-base pair. So how would that work? Well, actually, we're going to kind of pick on CH3COOH, that's acetic acid. CH3COO -1, that's acetate. So that's your conjugate acid-base pair. Let's see how this works. Well, if we go ahead and dump some H plus in there, what's going to happen then is that our H plus is going to be gobbled up by our conjugate base, acetate, to form acetic acid. Okay. So you can kind of see here, we're going to add acid, and we're going to still have our conjugate base to a certain amount, extent, but some of that has been changed to the weak acid. So it just it resists pH change. The other scenario is for that same buffered solution, if I were to add some hydroxide ion, what would happen is that now the weak acid, the CH3COOH, would gobble that up and form some acetate. So you can imagine that over here, I've got more acetate, and I've got less acetic acid, but it's fighting the pH change. There's actually a couple ways, if you have a buffered solution, there's a couple ways of coming up with the pH. And it's funny because I was like, you can use an ice chart, you really can. But I'm going to actually introduce something called the Henderson-Hasselbalch equation, affectionately called HH equation. And that's your HH equation. You see me refer to it. Okay. I'm trying to think. Yeah, you won't have an equation sheet. This is one that you're just going to want to memorize. When you use the Henderson-Hasselbalch equation, you use it for buffered solutions. And if you've been kind of following this that I have on the board here, basically all you got to do is know the molar concentration of your base, the molar concentration of your acid. The Ka you get from a table, then apply the P function to your Ka, and that would be the pH of your buffered solution. Okay. The problem, well, it's not really a problem, but we're going to be working some problems. You have to be careful that this base and this acid are conjugate acid-base pairs. That's why it was so important for your Part 6 homework that you guys are handing in. You need to be able to recognize, oh, that's a conjugate acid-base pair down there floating around. Okay? Actually, the Henderson-Hasselbalch equation is just a mathematical derivation of the Ka expression for a weak acid. And I'm not going to show you the derivation, but it is. So let's consider another form of the Henderson-Hasselbalch equation. And I'm going to kind of do a proof to show you why this works. What we know is the molar concentration to be the moles divided by the volume that those moles are swimming around in. The molarity of the acid would be the moles of acid divided by the volume that it's swimming around in. There's a good chance that that volume is the same. So honestly, this ratio right here then is the same as the molar ratio of conjugate base to acid is the same as the moles of base to moles of acid. Okay. So it just depends on what's kind of easier for you to work with. So that means then the other form of the Henderson-Hasselbalch equation looks like this, where instead of the molar ratio of the base to the acid, it's the moles of base to acid. So either one, Henderson-Hasselbalch. All right. So how does it work, or what does it need to be a valid buffered solution? Because I'll tell you right now that there are some, you can push a buffered solution beyond its limits, as you might imagine. Okay. So in order for the Henderson-Hasselbalch equation to work, there are some assumptions, and they're actually kind of assumptions that we've been talking about already. Remember when we said X is very small? Wait, no, X is very small. We said X is very small compared to the molarity of the weak acid. So the amount of ionized, that's X, the amount of ionization that the acid undergoes is very small. The amount of the hydrolysis that the base undergoes is also very small. And actually, the reason that buffered solutions work is we have a common ion effect in place. And so a significant amount of the conjugate base of the acid minimizes ionization of the base. The presence of the conjugate acid minimizes ionization of the acid. The common ion. All right, what else do you need to know about buffered solutions? Well, I'll go ahead and write the Henderson-Hasselbalch equation up here. So pH of your buffered solution will be equal to the pKa plus log of base 10. You can either go moles or molar concentration of the base to the acid. One of our daughters, she's grown now and all that, but she played the bass, bass. So every once in a while we I do bass, I spell it wrong, but anyway. Okay. So what's driving the pH then is going to be this ratio right here, because remember your pKa, you get that from a table. Either calculated or somehow, okay? So this is the kind of the living part of our buffered solution. Now there's this, and we'll talk a little bit about it, but buffering capacity is kind of how much you can dump into it and it still stays buffered if it's at pH. So your capacity depends upon the ratio of your base to acid, and it also depends on how concentrated they are. Here's how this works. Ideally, you get this ratio to be equal to 1. If it's not 1, 1 is ideal. It can be as small as 0.1 or as large as 10. Okay, that all works. If it's 1, check this out. If this ratio is 1, the log of 1 base 10 is actually 0. So if this ratio is 1, then check this out. Your pH is equal to your pKa. It's like math magic. Okay, so the closer to 1, the better. The larger the concentration of both, the better. So it's possible, like you have a, I don't mean to laugh or anything, but so say you go and you make a buffered solution and you have 0.00005 molar of your conjugate base and 0.00005 molar of your acid. It's not going to have much of a capacity because it's too liquid. And this was the kind of the 10 to 1. So you can have, this ratio can be as small as 0.1 or as large as 10, okay, and it still works. 1 is the best, like Goldilocks in the So let's see if we can read this. I was looking at this figure at home last night and I'm like, it's kind of silly. So we have a color indicator, and then we also have a pH probe, pH of 8.0. Notice we're going to add some acid. It's a buffered solution. So it budged the pH from 8.0 to 7.7. So it became a little more acidic. The point here is, and check out the volumes. Okay, so this volume, hard for me to tell. Yeah, I can see it kind of went up a little bit. Well, look at that. Like, dude, you think? Okay, so anyway, they basically doused their solution with even more acid, and at some point, again with our methyl orange, okay, it became red, showing me that it didn't have the capacity for that. You can read on the pH meter now, it's 1.53. That is actually it. So anyway, buffered solution resists change, but not beyond its capacity. So those are the 2 forms of the Henderson-Hasselbalch equation. I wonder if they were friends, you think? Or if you want to go check that. Okay. Maybe they just just sit and say, yeah, they do that in like in astronomy. There's a Henderson-Hasselbalch, that's the thing. There's a HR, Hirschsprung and Russell were the 2 scientists. Calculus, they say, was by Newton and Blair or something? I don't know. 2 people. Okay. So here's the deal. If ideally these are equal molar concentrations gives you a ratio of 1, which the log of 1 is 0, then ideally when you go looking for a good conjugate acid-base pair, you should basically try to get the Ka for your weak acid. The pKa of that should be equal to kind of, this is of your target pH. This is our target pH. Okay. Your acid-base concentrations, in order to have a little bit of oomph, should be 0.1 should be, this is greater than 0.1 molar. Otherwise, you're looking at something kind of just too wimpy to do what you have wanted it to do. This is what I kind of told you a minute ago, that we're looking for equal amounts of conjugate acid and conjugate base, that make that ratio 1, which makes this term 0. And that would mean that then your pH is equal to your pKa. I'm going to warn you that working these, you guys had, you will have. No, yes you did. In part 6, you guys did some kind of manipulating. If you know the Kb of the weak base, but you don't know the Ka of its conjugate, you guys know how to get that. Because for conjugate acid-base pair, the Ka times the Kb is equal to Kw. All right. So, yep. So, let's kind of look at the extremes. So this ratio can be anywhere from 0.1 to 10. So then what that means is that, for instance, if the ratio is, let's say you have 10 times more base than you have acid, then that ratio will be 10. That number becomes 1. So then your pH is actually going to be your pKa plus 1. If you have 10 times more acid than you do base, then you're going to have a ratio of 0.1. The log of 0.1 is -1. And so then applying the Henderson-Hasselbalch equation, pKa minus 1 is kind of what you're looking at for your target pH, or what the pH will be of that buffer solution. So if you kind of look at the two extremes, what we have here then is that your pH, your target pH will be within plus or minus 1 pH unit of the pKa. This is in its life. So how are we going to get that buffered solution? How are we going to get the conjugate acid and base hanging out together? The easy way is to physically mix some of each. That's the easy way. You just got the other way. That's not the other way. Another common way, though, is you have the acid or the base, the weak acid or weak base. You add strong base or strong acid to your weak base or weak acid, and you're made the conjugate. I'll show you how that works. Let's see. So these are the two ways of making a buffered solution. This one down here, see if I can do this. You take your weak acid, weak acid, come back, plus a strong base, and it will give you your conjugate base. The other one is you take your weak base and a strong acid, and it will give you your conjugate acid. Notice that on purpose I have a one-way arrow. It's a one-way ticket home. And we're going to work an example probably like this first one. And you have your weak acid, conjugate base, your weak base, and conjugate acid. I'm going to say all of the strong base, SB, and strong acid will be consumed. I'll show you what that is. All right, here we go. First one, let's do the easier of the two. How's that sound? So, It says, what is the pH of a buffered solution? Now, right there, you should say, buffered solution. I bet I'm going to use the Henderson-Hasselbalch equation, because it's a buffered solution. What will be the pH? And that will be this term here. If I go ahead and dump some sodium benzoate, sodium benzoate. So I'm hoping you guys recognize that this NaC6H5COO is going to split apart and give you an Na plus and a C6H5COO minus. And sometimes students will be like, well, how am I supposed to know that? Well, you're in chem food. Okay. So it is a one-way arrow. When it splits apart, it's a one-way arrow. And let's see the other thing. I'm going to over this guy over here, the C6H5COO minus. Hopefully you've done enough of these. Does that look like a weak acid or a weak base?
The one you just did, you mean?
Yeah, this guy. Yep, this is a weak base. You got it. So here in the Henderson-Hasselbalch equation, I'm going to go right there. And does this guy right here look like your conjugate weak acid? Because it totally is. Okay, so then all we got to do, I call it counting beans. We can either go with relative moles or molarity, and I think we're going to go with relative moles. Moles is going to be easier than molarity here. So all we got to get is moles of those two things. So here we go. This is just kind of an extra, for this problem, we really don't need to do this, but I'm doing it anyway. In the Henderson-Hasselbalch equation, we need the Ka, you need the Ka of your conjugate acid in your acid. Because there's a term, the pKa, right? How are we going to get pKa from Ka? How do we get pH from? Negative log. Yep, negative log will do it. But one of the things you guys did in part 6 was we can knock out the we can knock out the Kb from this by taking the Kw divided by the Ka. And your Kb is 1.6 times 10 minus 10. So Kb is equal to 1.0 times 10 minus 14th divided by your Ka, which is 6.3 times 10 minus 5th. 2 sig figs, 1.6 times 10 to the minus 10. Again, I'm a little apologetic because we're not going to use that number. But we are going to use this number. Okay. So here we go. This is what we're working with. There's a few ways to skin this cat. See how I did it on my notes. We're going to go with moles here just because basically we're going to, when we add our sodium benzoate, we've got grams, so we can use the molar mass to get to moles of the benzoate is the name for this C6H5COOH minus. Okay. I had to smile because actually I think I don't usually write my molar masses on my slides, but I did on this one. So let's go for the moles of the acetic acid that we have present. Or not the acetic acid, I'm sorry, the benzoic acid. So we had the volume, 500 milliliters, so with 3 sig figs, so 500 decimal milliliters. We have to go ahead and get that into liters. You know how to do that. 1 liter over 1,000 milliliters. I would probably put that term next. The molarity was the molarity is 0.100 moles per 1 liter. Now, there's a good chance if I label it moles of C6H5COOH, I wouldn't be as explicit there. Round to 3 significant figures, then the N, the moles of acid, are 0.0500. And, you know, if you're into such things, you know, that's going to be that term right there. sometimes working with problems, you're like, it just helps to see things. All right. So yeah, this is where I kind of giggled because I actually wrote out the molar mass. And I don't know why my blue is going away, but it is. So the molar mass of the sodium benzoate is 144.10 grams per mole. Yep, so the mass was the 21.61 grams. And then we use the molar mass, the flipped version of the molar mass, 1 mole over 144.10 grams. And again, I probably wouldn't write this, well, I guess I probably would write the species. Because that will give us moles of the whole salt, and we just want moles of that polyatomic anion. We just want moles of C6H5COO minus, which there's a 1-to-1 relationship there. So 1 mole of the C6H5COO minus for every 1 mole of C6H5COONA you have. So we're allowed 4 sig figs. So you're looking at 0.150 moles of figs. And that'd be like, is that within 1/10 of each other? And I suppose so. You multiply this times 10, you get 45. So I guess we're okay. All right. Again, this is the easier of the two, though. Ways of making a buffered solution. Okay, so there's our Henderson-Hasselbalch equation. Substituting in looks like this, where you guys told me to get the pKa, we're going to take the negative log of the Ka. Now, to me, I probably would kind of in my margin do pKa is equal to negative log of 6.3 times 10 to the minus fifth, and then plug that number in, just so you know when you look at how I work things. That's okay. And then we're going to add to that the log of the ratio of the base over the acid. So the log of the ratio of 0.150 divided by 0.0500. So yeah, I would probably figure this out because that's hard for me to put my calculator. But when you crunch it, you can double check this, but looks like we got 4.20 plus 0.48. And that will give you a pH of 4.68. That's it. That's the pH of that buffered solution. We good with that? I like the Henderson-Hasselbalch equation. I saw how in my author's answer key how you could do it with the ice table. Much better this way. Okay. Oh yeah, now I remember. All right, so now this is going after a different variable, very similar, well, different chemistry too. But notice, hopefully you're seeing that Na+, so probably think that's a salt, and it is. That Na+ is going to kick off. That'll give you a CH3COO negative plus Na+. One-way arrow. And then can you see where these differ by a proton? So I'm going to write WB for weak base here, this guy up here, I'm going to WA for weak acid. But this is a little different in that we have the target pH, okay, but we're supposed to see how many grams of sodium acetate, how many grams of moles of base we would need to add to this moles of acetic acid. Okay, so this is the variable we're after here. Again, this is kind of a step that we don't really have to do in this problem, because your Henderson-Hasselbalch equation here in a minute, we're going to take the pKa, it's going to be our first term. But we could knock out the Kb for this by Kb is equal to Kw divided by Ka. In this case, Kb is equal to 1.0 times 10 to the minus 14th divided by 1.8 times 10 to the minus 5th. 2 sig figs. It gives us a Kb of 5.6 times 10 to the minus 8 to 10. Okay, so there's a couple ways to work this. You can see what I'm doing is knocking out my first term there, so I got a real number. Applying the p function to 1.8 times 10 to the minus 5th, you get 4.74. So that's our pKa term. That just kind of made things. We're going to use that here in a minute. I can see now, that's a check to make sure that it seems reasonable. If our target is 5. Remember, our target pH plus or minus 1 pH unit, so that's fine. All right. So the Henderson-Hasselbalch equation, we know the pKa, we know the moles of acid, but we don't know the moles of the base. And we know the target pH unit. So rearranging this, we're trying to get to this guy right here, the molarity or the moles of the conjugate base. Of course, the first step would be to move the pH and the pKa on the same side of the equation. And I don't show you this step, so check this out. If I take 10 raised to the log base 10 of a quantity, that actually then is equal to this quantity. So in other words, if I take 10 raised to the power of each side, on the left side I get the molar concentration of base divided by the molar concentration of acid, and on the right hand side I get 10 raised to the pH minus pKa. It's kind of a nice, it's not a trick, but a nice little feature of logs. Because again, this is my unknown. This guy right here is what I'm trying to get to. Okay, so I'm trying to get to that guy. I can rearrange this now, and I can simply say that the molar concentration of the base then is equal to conjugate base is equal to molar concentration of acid times 10 raised to the pH minus pKa. All right, all we've done is rearrange the Henderson-Hasselbalch equation for the thing we're trying to get to. Now I have a slide here that says you probably, instead of molar concentrations, want to go for moles. Okay, so it's actually the other form of the Henderson-Hasselbalch equation. It's not a different form, but. So now if we rearrange this, now the moles of base we need is equal to the moles of acid times 10 raised to the pH minus pKa. And then life looks like a breeze now from there. Because we can use the volume and molarity to get to moles of acid. The target pH was 5.00. The pKa we came up with was at 4.72 or something like that. So here we go.
Did that just... Yeah.
Did.
No, but I read the wrong term first. Just like so.
Okay, so here we go. Moles of acid. 100 milliliters. Looks like I needed a decimal there. 100 milliliters. It is, I would use, my second term probably would be what it's third up here. So I put 100 milliliters, I put 1 liter over 1,000 milliliters, and then I would put the molarity 0.125 moles of CH3COOH per 1 liter of solution. Then give yourself 3 sig figs. And I get 0.0125 moles of CH3COOH. So that's my N of acid. So going back to our Henderson-Hasselbalch equation, rearranged, plugging in now, it looks like this, where the moles of base we need is equal to the moles of acid, which we just came up with was 0.0125 moles, times 10 raised to the pH minus pKa. The target pH was 5.00, and the pKa we came up with earlier was 4.74. Which is 3 sig figs, 0.0227 moles of CH3COO minus. So that's acetate. So now what we need to do is to see how we get those moles from the compound, the sodium acetate. So here we go. Looks like I shouldn't show the calculation of molar mass, but the molar mass for sodium acetate is 83.03 grams per mole. But before we do use the molar mass of the salt, we need to recognize that for every 1 mole of CH3COONA, we will have 1 mole of CH3, this is a subscript, CH3COO negative. And then we can use the molar mass of the salt that we're going to be adding, which if you use the periodic table, you'll come up with 82.03 grams of CH3COONA per 1 mole of CH3COONA. 3 sig figs, drum roll. So that means that you need to add 1.87 grams of the salt, CH3COONA, in order to get your system working right. Get the target pH. Let's see, today's Monday. That'll work. So I am going to hold the next one hostage. No, I'm going to hold the next one until that last problem until Wednesday, because we're doing fine for time in lecture, and then I want to give a little bit of time for this to settle, and we'll do the next one, okay, on Wednesday. You could do some homework, but it won't be due until Friday.